Good morning, dear students, and once again, welcome back to our course. In the last lecture, we started one of the most important topic from control system, that is nothing but signal flow graph. And I told you that why signal flow graph plays an important role and what is the application of signal flow graph. Basically, signal flow graph is nothing but a technique to represent the behavior of a system in the form of a graph where we have a combination of certain types of node, and each node is going to behave like a state variable in a given system. And we discussed in detail about how to obtain the signal flow graph for any system. The thing is that we need to apply very simple technique over there. First of all, the system to which we are interested to find the signal flow graph, first of all we need to obtain its mathematical modeling. Then once we have the mathematical modeling of system, then we need to identify the state variable, and we need to assign each state variable as a separate node. That is very important. Separate node. And then we need to indicate the flow of signal the way they are mentioned in the actual system. That is important. And then we solve some numerical on signal flow graph. For example, if the system is available in the form of physical, then how to find its mathematical modeling, followed by how to identify the state variable and how to assign each state variable as a separate node, and then how to indicate the flow of signal between the nodes. In the same way, if we have a mathematical modeling of a system directly, then how to uh, represent its signal flow graph. And then we discuss some basic terminologies which are commonly used while drawing the signal flow graph for any system. For example, we discuss the concept of input node. So what is input node? It is nothing but a node which is available in the signal flow graph which has only outgoing branches. That means this type of nodes has only outgoing branches. They don't have any incoming branches. In the same way, we discuss the concept of output node, which is also called a sink node or dependent node. What is output node? Output nodes are nothing but a type of node available in signal flow graph which has only incoming branches. They don't have outgoing branches. And then we discuss the concept of chain node, or they are also called as intermediate node. So this type of nodes has a combination of both incoming as well as outgoing branches. Then we discuss the concept of forward path. What is forward path? Forward path. So forward path means nothing but we are trying to move from input node to output node. That is nothing but what a forward path. Then we discuss the concept of path gain. Path gain means nothing but it is simply the product of gain of branches which are responsible for the formation of that particular path. So that is called as path gain. That is important. Path gain. And then we discuss the concept of loop. That is important. So I told you that in case of loop we have a combination of self loop and non self loop. Self loop means what? A type of loop which start from one particular node, end at the same particular node without having any other node apart from the reference node. So that type of loops are called as self loop. And one is called as non self loop, in which it will start from one particular node, end at the same particular node, and while traveling it is going to take care that it will going to entertain one more node apart from the reference node. That is nothing but the self node. In the same way, we define the concept of loop gain. So what is loop gain? It is simply the product of gain of branches which are responsible for the formation of that particular loop. Then we discuss the concept of pair of non-touching loop and pair of touching loop. Pair of non-touching loop means what? A loop which do not have any common node in between them. Those pair of loops are called as non-touching pair of loops. In the same way, if two or more than two loops have at least one common node in between them, that is called as a pair of touching loop. So all these points are very important in order to understand the concept of Mason's gain formula, because ultimately our second objective is how to obtain transfer function if we know the signal flow graph for a given system. That is our objective, and this is possible applying the concept of what? Mason's gain formula. So in today's session, we are going to discuss what exactly Mason's gain formula is and how Mason's gain formula plays an important role in order to determine the transfer function of system if its signal flow graph is known to us. Now, why we are interested to find the transfer function? Because of lot of advantages. For example, if you know the transfer functions, we can easily find out the stability of a system by applying Hurwitz criteria, Routh-Hurwitz criteria. If we know the open loop transfer function of systems, we are in a position to find out its root locus, through which we can easily find out the range of k for which the system is going to be stable, unstable, marginally stable. So a lot of things we can identify for a given system if we know its corresponding transfer function. So the first portion of this particular topic deals with how to obtain signal flow graph of a given system, that we have done. The second part of this particular section deals with, if we know the signal flow graph of a system, how to convert that signal flow graph into its corresponding transfer function, or how to obtain transfer function if we know the signal flow graph for that particular system. That is very important. So that is nothing but the application of what? Mason's gain formula. So let us start our today's session, where our objective is to understand the theoretical aspect of what exactly Mason's gain formula is and how it is applicable to determine the transfer function of a system if its signal flow graph is known to us. Now, first of all, we are going to discuss the history of signal flow graph. So, the concept of signal flow graph was originally invented by Professor C. Shannon. He was basically an American mathematician, electrical engineer, and cryptographer. He is also known as the father of information theory. And the process of deriving the parametric function, which is also called as transfer function, from signal flow graph was first of all introduced by Professor C.J. Mason. And that's why this particular technique is called as Mason's gain formula, because by applying this particular formula we are in a position to find out the overall gain of the system. That means the parametric function of the system through which we are in a position to define the system behavior. And this technique was first introduced by Professor C.J. Mason. That's why it is called as Mason's gain formula. And he is an American electronic engineer, and he gave a mathematical formula to determine the transfer function of a system whose signal flow graph is known to us. That is important. So this is what the basic history of what exactly signal flow graph is, and which are the persons which are responsible to uh, make a conceptualization of this particular theory. So the main person behind signal flow graph theory, that through SFG we are in a position to find out the transfer function of the system, is nothing but Professor C.J. Mason. And that's why this particular technique is called as Mason's gain formula. And through Mason's gain formula, we are in a position to convert signal flow graph of a system into its corresponding transfer function. That is very important. I hope this point is clear to everyone. Now, let us try to understand what exactly Mason's gain formula is and how this formula plays an important role to find out the transfer function of a system if its corresponding signal flow graph is known to us. Now, this formula is used to find out the overall transfer function of a system if its signal flow graph representation is available with us. And according to Professor the Mason's gain formula to find out the overall transfer function of a system is given by C of s by R of s. This is going to be equals to summation I vary from 1 to n pi delta I divided by delta. Now this is the formula through which we can identify, we can derive the transfer function of a system whose signal flow graph representation is available with us. Now in this formula, this C of s indicate the Laplace transform of response, which is nothing but output, and this R of S indicate the Laplace transform of input, which is nothing but the excitation, or you can say reference input. So I told you that transfer function is basically the ratio of Laplace transform of output by Laplace transform of input. That's why here it is written that TF is nothing but C of S by R of S. Now according to Mason's gain formula, this transfer function is nothing but summation I vary from 1 to n pi delta I divided by delta. Now what exactly p, what exactly delta, what is this I indicate, and what exactly this delta I indicate, that we are going to discuss in detail. Now in this equation, this n, capital N, indicate number of forward path or paths available in the signal flow graph. Now, in the previous lecture, we discussed that what exactly the concept of forward path is. So, forward path means what? A path where we are trying to move from input node to the output node. And while traveling, we do not need to disturb the flow of signal. That means we need to take care of only those branches which are having the flow of signal from input side to output side. That is important. So first of all, we need to identify that in a given signal flow graph, how many number of forward paths are there. And suppose in the given signal flow graph, the number of forward paths are 2, then in that case the value of n is going to be 2. That means to obtain the transfer function of that particular system via signal flow graph, we need to vary the value of n up to 2. That means the value of I is going to vary in the fashion like 1, then 2. Why? Because the value of I is going to vary from 1 to n. Now in this case, because we have only two forward path, that's why the value of n is going to be equals to 2. Hence the value of I is going to take two intermediate value. First one is 1 and second one is 2. So in that particular case, this formula is going to rewritten like P1 into delta 1 plus P2 into delta 2 whole divided by delta. That is important. I hope this point is clear to everyone. How to change this particular formula, because this formula is very general formula, because depending upon how many number of forward paths are available in the circuit, we need to define the value of n, and based on this value of n, we need to redefine this particular formula. That means at what particular point we need to terminate this formula. That means p1 delta 1 plus p2 delta 2 plus p3 delta 3 and so on. So for an example, if in a given system we have only two forward path, then in that case the formula is going to be like p1 delta 1 plus p2 delta 2 whole divided by delta. In the same way, in some cases we may have three forward paths. The thing is that we need to carefully identify that how many number of forward paths are there in a given system, and once we identify that, then it is very simple for us to redefine this formula. Now what is this p? P stand for the gain of forward path. P stand for gain of forward path. Now what is pi stand for? Pi stand for gain of ith forward path. Now what is the meaning of this? I told you that we discussed in detail about how to find the gain of forward path. Gain of forward path means what? It is simply the product of gain of branches which are responsible for the formation of that particular path. Now here pi indicate the gain of ith forward path. In the same way, for example, in our numerical, suppose we have only two forward path, so we need to find the value of p1 as well as we need to find the value of p2. Now what is p1 indicate? P1 indicate the gain of first forward path. First forward path. Now, whatever the path which we have chosen as a first forward path, gain of that particular path is indicated by P1. In the same way, if we have second forward path, whatever the gain of that particular path, we define that particular gain as second forward path. So P indicate gain of forward path and I indicate the number of that particular forward path. Suppose we are calculating the gain of first forward path, then it is going to be P1. Suppose we are going to calculate the gain of second forward path, it is going to be P2. So P indicate gain of forward path. Now what is delta? Delta indicate system determinant. Delta is nothing but what? System determinant. And how to calculate the value of system determinant, that I'm going to explain in the coming slides. But right now let us consider that delta is nothing but system determinant. And what is delta I? Delta I indicate the system determinant corresponding to ith forward path, where we need to take only those loop which are not going to have any physical contact with ith forward path. So what is delta I? Delta I is nothing but system determinant corresponding to ith forward path. So again it is going to be like system determinant corresponding to ith forward path. That is important. Now how to calculate this delta and how to calculate this delta I, that we are going to learn in detail. But for time being, let us consider that this is what the formula is through which we are in a position to obtain the transfer function of a system if its signal flow graph is known to us. And the formula is very simple. And according to Professor Mason, this formula is C of S by R of S is going to be equals to summation I vary from 1 to n pi delta I whole divided by delta. This is very, very important. Now, the same thing is mentioned over here. What is C of S? C of S is nothing but controlled output of the system, which is in frequency domain. R of S indicate the reference input of the system. Then N indicate the number of forward paths. Pi indicate the gain of ith forward path. Delta indicate the system determinant. And this is the formula to calculate system determinant. So delta, which is nothing but system determinant, is given by 1 minus. Now this formula you have to remember that how to calculate the value of system determinant. So it is going to be like 1 minus summation of all individual loop gain. So from this first statement, it is very clear that in order to find the value of delta, what we need to do, we need to first identify that how many number of loops are there in the given signal flow graph. So we need to identify and calculate their gain. For example, we have say two loops in the signal flow graph. So we need to find out their loop gain. So L1 indicate the loop gain of first loop, L2 indicate the loop gain of second loop. So in order to calculate the value of delta, what we need to do, we need to find out how many number of loops are there, and then we need to identify their gain. Now how to calculate gain of loop, that I already told you in the previous lecture, that it is simply the product of gain of branches which are responsible for the formation of that particular loop. So we need to calculate the value of loop gain L1 and L2. It is not at all necessary that in the signal flow graph there will be always two loop or three loop. That depends upon the structure. But it is very clear that in order to calculate the value of delta, we must know how many number of loops are there, and we also know what will the gain of that particular loop. So 1 minus summation of all individual loop gain, then we need to take plus summation of gain product. This is very important. Gain product of all possible two non-touching loops. That means now in this case we need to identify that if we have two loops, whether they are touching or non-touching. If they are non-touching, then we need to take the product gain of those two non-touching loop, and that gain you need to place in this particular bracket. In the same way, we need to take minus. The thing is that here the sign is going to alternate. First it will start from negative, then positive, and then negative. So this sequence you have to remember: 1 minus, then plus, and then again going to be minus. Now in this particular bracket, what we need to do, we need to identify that if we have a pair of three non-touching loop or not. If we have a pair of three non-touching loop, then we need to multiply the gain of those loops and put together inside this particular bracket. So in this way, suppose if you're interested to find what will be the next bracket, so it is going to be plus in bracket summation of gain product of all possible four non-touching loop. So here we need to take four non-touching loop and so on, and the formula keeps on repeating. Then here we need to take minus, then in bracket it is going to be like summation of gain product of all possible five non-touching loop and so on. So this is what the basic general formula that we can implement in order to find the value of delta, which is called as system determinant. I hope this point is clear to everyone, and this is the most important point to apply signal flow graph or Mason's gain formula to find its corresponding transfer function, because the formula is very simple, that in order to find the value of transfer function to signal flow graph, the formula is tf is going to be equals to like summation I vary from 1 to n. It is going to be like pi delta I whole divided by delta. Now we know the value of n, which indicate number of forward path. We know the value of p, which indicate the gain of forward path. If we are calculating for p1, it is indicate the gain of first forward path. If we are calculating for 2, this indicate gain of second forward path. Then delta is very important, which indicates system determinant. And uh, how to calculate system determinant? This is the formula to that for that. 1 minus summation of all individual loop gain. That means here first of all we need to identify that how many number of loops are there. So number of loops are very important, and then we need to calculate the gain of each loop. That is again very important, like L1, L2, L3 and so on up to Ln or Lk. And then we need to identify that how many number of pair of two non-touching loops are there, then three non-touching loops are there, then four non-touching loops are there, and based on that we need to manipulate this particular formula to calculate the value of system determinant. This is very important. Now how to calculate this delta 1, or you can say delta I? So delta 1, again we need to use the same formula, but the thing is that while calculating the value of delta 1, we need to take only those loops, maybe individual loop, maybe a pair of two non-touching loop, or maybe a pair of three non-touching loop that is not in physical contact with the first forward path. This is very important. So while calculating the value of delta 1, we need to take only those loops which are not in physical contact with first forward path. This is very important. In the same way, suppose we are interested to calculate the value of delta 2. The same formula we need to implement, which is nothing but delta. But the thing is that while calculating the value of delta 2, whatever the loops which we are going to take that is not in physical contact with the second forward path, that is important. So suppose in the structure of signal flow graph, we identify that my second path is flowing from x1, x2, x3 and x4. So no loop is going to be there which encountered the node which are in common with that particular forward path. Only those particular pair of loops we need to take care while calculating the value of delta 1, delta 2 and so on. That's why in most of the cases the value of delta 1 is, or delta 2 is going to be 1. Or if we have a pair of loops which are not in physical contact with the corresponding forward path, only those pair of loops, or you can say only the gain of those pair of loops we need to take care while calculating the value of delta 1 or delta 2. The thing is that if we solve some numerical on this, then only you can understand what exactly delta is and how to calculate the value of delta corresponding to delta 1 and delta 2. So the same thing is mentioned over here. See, we need to apply the same formula, but let me erase this. So while calculating the value of delta I, again we need to apply the same formula, but we have to take only those loop gains in calculations. See, yeah, we need to apply the same formula to calculate the value of delta I, but we need to take only those loops gain in calculations which are not in touch with the ith forward path. This is very important. The same thing which I just explained you, the same thing is mentioned over here. Now let us try to understand what are the different steps which we need to follow in order to obtain the overall transfer function of a system by applying Mason's gain formula. So the first step is we need to identify the number of forward paths available in the given signal flow graph, because we need to make the general representation of formula into a specific formula. That means uh, to what extent we need to vary the value of I, whether we need to take the value up to 2 or up to 3 or up to 4, that first of all we need to identify, and that depends upon the value of n, and n defines the number of forward paths available in the signal flow graph. That's why the first step to determine the overall transfer function using Mason's gain formula, if the signal flow graph is known to us, is nothing but identify the number of forward paths available in the given signal flow graph. That means identify the value of n. Then second step is we need to calculate the forward path corresponding to the given path. For example, if we identify that the value of n is nothing but 2, that means we have two forward path. So we need to calculate the gain of each forward path. That means we need to calculate the value of p1, we need to calculate the value of p2, and so on. So second step is we need to calculate the gain of respective forward paths indicated by symbol p1, p2, and so on. Then in step number 3, we need to identify how many number of loops are there, and we need to calculate their corresponding gain, which are indicated by symbol L1, L2, and so on. Why we need to identify how many number of loops are there and why need to calculate their gain? Because we need to calculate the value of system determinant, maybe delta or maybe delta 1, delta 2, and so on. Then in step number 4, what we need to do? We need to calculate the system determinant, like delta corresponding to overall system determinant, followed by delta 1, delta 2 corresponding to the first forward path, second forward path, and so on. And then we need to apply the Mason's gain formula in step number 5 to determine its overall transfer function. So these are a very simple steps which we need to follow in order to obtain the transfer function of a system if the signal flow graph is known to us. So in step number 1, identify the number of forward paths. That means we need to identify the value of n. Then in step number 2, calculate the gain of each forward path indicated by symbol P1, P2, and so on. Then in step number 3, we need to identify that how many number of loop gains are there, like L1, L2, and so on. Then in step number 4, we need to calculate the system determinant indicated by symbol delta, delta 1 and delta 2. And finally, we need to apply Mason's gain formula to find out its overall transfer function. So it is going to be like C of S by R of S is summation I vary from 1 to n pi delta I divided by delta. So up to step number 4, we identify the value of n, we calculated the value of p1, p2, p3, we calculated the value of delta 1, delta 2, delta 3. We also determine the value of delta. The thing is that we need to put all those components in this particular equation to find out the value of transfer function. This is very important. So I want you to please note down these points because this is very important to solve numerical on Mason's gain formula. These steps are very important. Step number 1, 2, 3, 4, and 5. So please note down this particular steps. The formula is very important, and this formula deals with the conversion of signal flow graph into its corresponding transfer function by applying the concept of Mason's gain formula. Once you have done with this, now let us try to solve some numerical on Mason's gain formula. Numerical on Mason's gain formula. So the first numerical on Mason's gain formula is determine the overall transfer function of a system represented by a following signal flow graph using Mason's gain formula. So signal flow graph for the system is given to us and it is shown over here, and our objective is to find its corresponding transfer function using Mason's gain formula. So how to solve this numerical? Now let us first of all identify the concepts which we have discussed in the previous class. That means what is node, what is input node, what is output node, what is intermediate node. Then identify that how many number of forward paths are there, what will be the gain of those forward path, how many number of loops are there, what will be the gain of those loops. That we are first discuss and then we will solve the numerical. So here, if you see the diagram very carefully, here we have total 6 nodes indicated by symbol y1, y2, y3, y4, y5, and last one is y6. Now, this y1 we can treat as input node. Input node. Now, why it is called as input node? Because it has only outgoing branches. In the same way, this y6 we can treat as output node. Now, why this called as output node? Because it has only incoming branches. I hope these points are clear to everyone. If not, just go and watch the previous lecture. In that case, I have discussed in detail about what exactly input node is and what exactly the output node is. Now, this y2, y3, y4, y5 are called as intermediate node. or chain node. Why? Because they have a combination of both incoming node as well as outgoing node. So these points are, I hope, clear to everyone. Now let us try to identify that how many number of forward paths are there. Now I told you that how to identify that forward path. Forward paths are nothing but we need to move from input node to the output node, and while traveling we are not going to disturb the sense of flow of signal in a particular branch. That means we need to identify and we need to select only those branches which are allowing us to move from input to output. That is important. So if you apply that logic, let us try to start our journey from first node, which is nothing but the input node. So we are at y1. Now we will move from y1 to y2 through this particular branch of gain exactly equals to a. Then from y2 to y3 we have two possible paths. First one is by taking a branch of gain b, and second one is by taking a branch of gain j. But I told you that while traveling from input to output, we need to identify, we need to take only those branches in which the signals are by default moving from input to output. Now in this case, if you take the second branch, that means from y2 to y3 we are moving, if through this particular path, we are not supposed to do that. Why? Because the signal is moving in the opposite direction. So this is not the perfect path, or this is not the perfect forward path to move from y2 to y3, because we need to take the sense of flow of signal in that branch, and it is always from input side to output side. So while moving from y2 to y3 we have only one branch of gain exactly equals to b, because the flow of signal is from y2 to y3. That is important. So y1 to y2 through a, and then from y2 to y3 only through b. We don't have the option to go through j. And then from y3 to y4, y3 to y4 we have a branch of gain c. And then again from y4 to y5 we are not in a position to select this path because the flow of signal is in reverse direction. So we have only one branch of gain exactly equals to d. And then from y5 to y6 again we have only one branch of gain exactly equals to e. So the first forward path is like y1 to y2 through a, then y2 to y3 through b, then y3 to y4 through c, and then from y4 to y5 through d, and then from y5 to y6 through e, like a b c d e. So a b c d e will be the gain for first forward path. So here we identify that the first forward path is like y1 to y2, then y3, then y4, then y5, and finally y6. And what will be the gain of this forward path indicated by symbol p1? It is going to be equal to, I told you that what is gain? It is simply the product of gain of branches which are responsible for that particular path. So here we have identified that the gain of branch available between y1 y2 is nothing but a. So here we need to take a multiplied by gain of branch between node 2 and 3 is nothing but b. So here we need to take b. In the same way, this will be c, this will be d, and this will be e. So a b c d e will be the gain of first forward path, which is nothing but the value of p1 as far as Mason's gain formula is concerned. I hope this point is clear to everyone. In the same way, let us try to identify that apart from this, whether we have one more forward path in the circuit or not. Now see, starting from first node, then we are moving towards the output node. We will reach at y2 through gain A, and then from y2 to y3 through gain B, and then from y3 directly, suppose if we select to move at y5, so we have basically two paths. we may select a branch of gain G, or we may select a branch of gain H, but this is not the desired forward path, because in this case the flow of signal is in reverse direction. See, the signal is flowing from output to input, but we are deciding the forward path, and I told you that in forward path we need to identify only those branches whose gain are from input to output. That is important. So here what we need to do, we need to take only this forward path, that means from y3 directly to y5 through gain G, and then from y5 to y6 we are going to follow this particular branch of gain exactly equals to E. So this will be the second forward path. So how we can write the second forward path? So it is going to be like y1 to y2, and then from y2 to y3, and then from y3 directly to y5, and then from y5 to y6. And what will be the gain of that particular forward path, indicated by symbol P2? So it is going to be equal to A into B, and then multiplied by G multiplied by E. So ABGE will be the gain for second forward path. I hope this point is clear to everyone. So here we have two forward paths. Let us try to identify that whether we have one more forward path in the circuit or not. So y1 to y2, y2 to y3, y3 to y5, then coming back to y4, and then coming back to y5, not possible. So here we have only two forward paths. Only two forward paths. That means the value of n is going to be 2. So what will be the exact formula to calculate the value of transfer function in this case? So it is going to be like summation I vary from 1 to n, but n is going to be t2, so I is going to be like 1 to 2. So the formula is like p1 delta 1 plus p2 delta 2 whole divided by delta. So this will be the general, or you can say exact formula to calculate the transfer function for this particular case, because here we have only two forward paths. P1 indicate the gain of first forward path, P2 indicate the gain of second forward path. Now how to calculate this delta, or delta 1 or delta 2? To calculate the value of this delta, or delta 1 or delta 2, first of all we need to identify that how many number of loops are there. Let me erase this. So in this case we need to identify that how many number of loops are there. So this will be your first loop, like this. So what is loop? We need to start at one node, then come back to the same node, and while traveling, if we had encounter one more node, then it is called as non-self loop. So here this is your first loop. So what will be the gain of that particular loop? It is simply the product of gain of branches which are responsible for the formation of that particular loop. So this loop is formed by two branches. First one is from y2 to y3 via branch of gain B, and then from y3 to y2 via branch gain J. So B into J will be the gain for first loop. In the same way, let us try to identify that whether we are having one more loop or not. See, this will be your second loop, loop number 2. And what will be the gain of that particular loop? It is simply the product of D into I. Then this will be your third loop, L3, and this is going to be the self loop having a gain F. Now here we have one more loop like this. If you start from y3, then move to y4, then reach at y5, and then coming back to y3, like this. through this particular branch of gain exactly equal to what? H. So this will be your loop number 4. That will be like C into D multiplied by H. In the same way, here we have one more loop. See, starting from Y3, if you move and reach to Y5, and then from Y5 coming back to Y3. So the gain of loop number 5 is going to be like G into H. Apart from this, I think we don't have any further loop in this particular case. We will not select this as a loop. Why? Because here we can move from Y3 to Y4 and from Y4 to Y5, but we cannot move from Y5 to Y3 like this. Why? Because the actual flow of signal is from Y3 to Y5. So we have to maintain the flow of signal in the branch. We are not supposed to disturb the flow of signal. That is important. So according to me, in this case here we have total 5 loop, out of which 4 loops are non-self loop and only one loop is self loop. Why? Because here if you see loop number 3, it will start at node 5, end at node 5, and while traveling it is not going to take care of any other node in its path. That's why it is called a self loop. Whereas if you see L1 or L2 or L5 or L6, all are nothing but your non-self loop. So this is very important. And once you identify that how many number of loops are there, say L1, L2, L3, L4, L5, then we need to identify that uh, a pair of non-touching loop, a pair of two non-touching loop, and so on. So let me erase this. Now in this case, see, we identify that we have total 5 loop, like this indicate L1, here this indicate L2, and then this bigger one indicate the L3, or you can say this indicate the L3. So this will be your L4, and the outer one will be the L5. Now we need to identify that pair of non-touching loop, 3 non-touching loop, and so on. Now see, pair of non-touching loop means what? The loop which do not have any common node in between them. For example, if you take loop 1 and loop 2, they are a pair of non-touching loop. Why? Because loop 1 is formed between y2 and y3. See, I'm writing over here, loop 1 is formed between y2 and y3. Whereas if you see loop number 2, it is formed between y4 and y5. So in between loop 1 and loop 2, we don't have any common node. That's why loop 1 and loop 2 are the pair of non-touching loop. Non-touching loop, or you can say these are the pair of two non-touching loop to be exclusive. In the same way, if you see loop number 1 and loop number 3, see, loop number 1 is formed between y2 and y3, whereas loop number 3 is formed at y5. See, we don't have any common node in between these two loops, hence this is the another pair of two non-touching loop. Non-touching loop. I hope this point is clear to everyone. The way I'm identifying that whether they are touching loop or they are non-touching loop is very important. In the same way, if you see loop number 1 and loop number 4, they are going to be a pair of touching loop. So we don't need to identify pair of touching loop. We need to identify pair of non-touching loop. It may be 2, it may be 3, it may be 4, or it may be anything. So if you see loop number 1 and loop number 4, they have a common node in between them, and that node is 3. You can also write over here like loop 1 is formed between y2 and y3, and loop number 4 is formed between y3, y4, y5, and then coming back to y3. So see here, this y3 and here this y3 is common. Hence loop 1 and 4 are a pair of touching loop. So ignore them. In the same way, if you see loop number 1 and loop number 5, so loop number 1 is formed between y2 and y3, and loop number 5 is formed between your y3 and y5. So see, 3 3 is common. Hence this is the pair of touching loop. So no need to take care. So if you apply that logic, we can easily find out that how many number of loops are a pair of non-touching and how many loops are a pair of touching. Touching, we don't need to take care, because while calculating the value of delta, or say delta 1 or delta 2, we need to take care of only those pair of loops which are non-touching with respect to each other. That is important. So if you understand this, now it is very easy to apply Mason's gain formula to find out its corresponding transfer function. So our objective is, we want to calculate the transfer function of the system using Mason's gain formula. So first we identify that how many number of forward paths are there, then we calculate their gain, then we identify that how many number of loops are there and we have calculated their gain, and then we identify that pair of two non-touching loop and three non-touching loop, and then we need to apply Mason's gain formula. So the same thing is mentioned over here. See, first step, according to Mason's gain formula, the overall transfer function is given by. This is what the general representation. So this is what the general formula to calculate the value of what? Transfer function. Now we need to identify in step number 1 how many number of forward paths are there. So with respect to the given signal flow graph, we identify that there are total 2 forward paths. That means the value of n is going to be 2. And now we need to redefine this formula based on our structure. So the actual formula to calculate overall transfer function for the system is given by C of s by R of s is going to be summation I vary from 1 to 2. Now instead of taking n, here we need to take n equals to 2. So it is going to be like pi delta I divided by delta. And if you apply that logic, we can write here as C of s by R of s equals to p1 delta 1 plus p2 delta 2 divided by delta. Let this will be your equation number 1. Now from equation 1, it is very clear that in order to calculate the value of transfer function, what we need to do, we need to find the value of p1 p2, find the value of delta 1 delta 2 and delta, put all those value in equation 1. We can easily find out the value of transfer function. That's it. Now step number 2, we need to calculate the gain of forward path. So this is what the structure which is given to us, and here we identify the number of forward paths are 2. The gain of first forward path. So first forward path is formed between y2, y3, y1, y2, y3, y4, y5 and y6. The straight path like this. So as I told you that the gain is p1, and it is simply the product of gain of branches which are responsible for its formation. So it is going to be like A multiplied by B multiplied by C multiplied by D then multiplied by E. That's it. That this will be equation number 2. In the same way, we identify the second forward path, and it is formed between y1, then y2, y3, directly from y3 to y5 through this particular path. See, y1, y2, y3, and then from y3 directly to y5, and then from y5 to y6. And what will the gain? It is simply the product of gain of branches which are responsible for its formation. So it is going to be like A multiplied by B multiplied by G multiplied by E. See, so P2 is going to be your A, B, G, E. That this will be your equation number 3. So in step number 2, we need to calculate the gain of forward paths that we have calculated. We identify in step number 1 that here we have two forward paths, n1 and n2, and then in step number 2 we need to calculate the gain of those forward paths p1 as well as p2. Now in step number 3 we need to do the calculations for loop gain. As I told you that here we identify total 5 loops. So let us try to indicate them. So the loops are like L2, L3, then coming back to L2. This will be a first loop. See, L2, L3, and then coming back to L2. This will be your loop 1. So this will be your loop 1. Then second loop is L3, L5, and then coming back to L3. See, L3, then L5, and then coming back to L3. This will be your loop number 2. This will be your loop 2. And then third loop L3, L4, L5, then coming back to L3. See, L3, L4, L5, and then coming back to L3. This will be a loop number 3. So this will be loop 3. And then loop 4 is L4, L5, and then coming back to L4. This one. L4, L5, then coming back to L4. This will be a loop number 4. So this will be L4. And then last one is self loop. Starting from L5 coming starting from Y5 coming back to Y5. So this will be your loop number 5. Now what will the gain for each loop? See, gain means what? We need to multiply the gain of branches which are responsible for the formation of that particular loop. So same thing is mentioned over here. L1 will be B into J. See, B multiplied by J. That's it. In the same way, L2 will be your G multiplied by H. The sequence you may take anything. You may write this as H into G, or you may write this as G into H. You may take this will be your loop number 4, or you may take this will be your loop number 1. That doesn't matter. The thing is that we need to carefully identify that how many number of individual loops are there, and we need to carefully obtain their loop gain. That is important. In the same way, if you apply the logic, we can find out the value of L3, L4, and L5. Now, in step number 4, what we need to do? We need to calculate the system determinant. Now, this is important. Now, system determinant, we need to identify that how many number of pair of two non-touching loops are there, and we identify that already here we have two pair of two non-touching loop. So first pair of non-touching loop is your y2, y3, then y2. This will be your loop number 1, followed by y4, y5, and then y4. So I think this will be your loop number 4. Yeah. So loop number 1 and loop number 4 are a pair of non-touching loop. So what will be the gain product of these pair of non-touching loop? The thing is that we need to multiply their gain. So what is the gain of loop 1? See, L1, loop 1 gain is B into G. So it is going to be B into J. Then what is the gain for loop 4? It will be simply D into I. So what we need to do? We need to multiply B into J and D into I. So it will be like BJDI. This will be the gain product of first pair of two non-touching loop. In the same way, we have identified that there will be one more loop or one more pair of two non-touching loop, and that is loop number 1, and I think the self loop. Let me check what is the number for self loop. It is loop number 5. Okay, so loop number 5. So what is the loop gain of first loop? It is nothing but B into J. And what is the gain of loop 5? It is simply F. So what we need to do? We need to multiply them, Bj into F. I hope this point is clear to everyone. Why we have calculated this point? Because this plays an important role to calculate the value of delta, delta 1, delta 2, and so on. We required the pair of uh, loops, that two non-touching loop, and then we need to calculate the product of, or you can say gain product of pair of two non-touching loop, gain product of pair of three non-touching loop, gain product of pair of four non-touching loop, and so on. So to calculate the value of delta, we require these terms. That's why we have calculated them earlier. And then in this case, the pair of three non-touching loop is no. That's why the gain product is going to be 0. So the formula to calculate the value of delta is restricted like this. So it is going to be like delta is going to be 1 minus summation of individual loops. So it is going to be like L1 plus L2 plus so on up to L5. Then minus, here we need to take gain product of two non-touching loop. So it will be like L1 L4 plus L1 L5. Then this is going to be plus, then minus gain product of three non-touching loop, because we don't have three non-touching loops, that's why this is going to be 0. So the formula to calculate delta is restricted to this particular term only. This is important. Now if you apply that logic, we can easily find out the value of system determinant according to Mason's gain formula. Now if you substitute the value, we can find out very easily. See, in this case, delta is going to be 1 minus summation of individual loop gain. So we have total 5 loop gain like L1, L2, L3, L4 and L5, and then plus uh, gain product of pair of two non-touching loops. So this will be your first pair of two non-touching loop. I think it is L1 and L4, and I think this will be L1 and L5. So that is important. So we have calculated the value of delta. Let this will be the equation number 4. I hope this point is clear to everyone. And then we need to calculate the system determinant corresponding to first forward path and second forward path. Now see here, what is first forward path? This will be your first forward path. And while calculating the value of delta 1, what we need to do? We need to apply the same formula, that is 1 minus summation of loop gain of individual loop. But we need to take care of only those loop which are not in touch with this particular forward path. So आपने आइडेंटिफाई करना है ऐसे लूप्स को जो कि आपके फर्स्ट फॉरवर्ड पाथ को टच नहीं करते. तो ऐसा कोई भी लूप नहीं है जो आपके फर्स्ट फॉरवर्ड पाथ को टच नहीं करता. That's why this is going to be 0, and hence the value of delta 1 is going to be 1. I hope this point is clear to everyone. In the same way, if you are interested to calculate the value of delta 2, again you need to use the same formula. 1 minus summation of individual loop gain, then plus in bracket gain product of two non-touching loop, and then plus or minus gain product of three non-touching loop. But while taking the loop, we need to identify that, or we need to take only those loop which are not in touch with your second forward path. अब second forward path आपका क्या है? ये है, यहाँ से शुरू किया एंड देन यहाँ पे आए एंड देन यहाँ पे. अब यहाँ पर आप देखोगे तो हर एक लूप आपका सेकंड फॉरवर्ड पाथ को कहीं ना कहीं टच कर रहा है. फॉर एग्जांपल लूप 1 आपका y2 और y3 पे टच कर रहा है. देन लूप 2 की अगर आप बात करोगे तो वो फिर y3 और y5 पे टच कर रहा है. लूप 3 की अगर आप बात करोगे तो वो y3 y5 पे टच कर रहा है. लूप 4 की बात करोगे तो वो y5 पे टच कर रहा है. लूप नंबर 5 की बात करोगे तो वो y5 पे टच कर रहा है. दैट मीन्स there is no single loop available in the structure which is not in physical contact with the second forward path. Hence the expression for delta 2 is going to be like 1 minus 0. So it is going to be like 1. I hope this point is clear to everyone. So if you apply this logic, the value of delta 1 is going to be 1. Let this will be the equation number 5. The value of delta 2 is going to be 1, which will be your equation number 6. Now in step number 5, we need to calculate the overall transfer function. So from equation number 1 to equation number 6, we calculated the terms which are required to calculate the overall transfer function of the system using Mason's gain formula. Now we need to club all those equations and put them into general expression. So from equation 1 to 5, we can write Overall transfer functional system is like C of S by R of S going to be P1 delta 1 plus P2 delta 2 divided by delta. So put the value of P1, P2, delta 1, delta 2 and delta in this equation, solve, you will get this as an output. So this indicate the overall transfer function of the system using Mason's gain formula. This is very important, and this is your transfer function. So this is what the way we can apply Mason's gain formula to convert signal flow graph into its corresponding transfer function. I hope this is clear to everyone, and if you understand this, now it is very easy for you to solve any numerical on signal flow graph. The thing is that you should know what is Mason's gain formula and how we can apply Mason's gain formula to find out the transfer function for given signal flow graph. In the next lecture, we are going to solve some more numerical on Mason's gain formula, where we are going to take care that if you know the representation of system in the physical form or in the mathematical form, then how to apply that logic to find out its corresponding transfer function using Mason's gain formula. Thank you.